It's my turn to introduce my dear friend, Professor Karen Scrivener. She's a professor and the head of the Laboratory of Building Materials at the EPFL, the École Polytechnique Fédérale de Lausanne. And she has been the spirit and the main coordinator of the LC3 project. I have been working with her since 2005, and she was also the mastermind behind the international research network NanoSem that was, coordinating the industry and the academia in the research of fundamental research related to cement. So you can say that this collaboration brought up the cement to the international arena in the scientific world. And she is also a member of the UK Royal Academy of Engineering and co-author of more than 200 papers. With this, Karen, thank you very much for joining us online. And she decided not to send a recording, but to make an online presentation. So I give you the floor for the presentation, and afterwards I will moderate the questions of the people. Thank you, and please start.
Hello, hello. Right, you hear me now?
Yes. Yes. Yes.
Can you confirm if you can hear me first?
Yes, we can hear you, Karen. We can hear you.
Okay, good. Sorry about that glitch. Okay, so very pleased to join you all from Switzerland. Very sorry not to be there. I'm very pleased to find the opportunity to address you today. So I'm just going to introduce the topic of LC3, but I really want to stress at the outset that the real interesting thing about this technology, it can be done, first of all, fast. We were just talking about the need for speed, and I'm sorry, the need for speed is essential because in less than 7 years, we will already exceed the amount of CO2 that can lead to a temperature rise of more than 1.5 degrees. So we have to go fast, and we have to go at large scale. It's no use having fancy cement solutions, which can only be used in a few places. We have to have solutions that can be used everywhere. So first and foremost, we really have to realize that we can't do without cement and concrete. They are making up about 2/3 of all the materials we use. This is not just in construction, this is in everything, okay? So, particularly here in Europe, people say, oh, we stopped using concrete, we build everything in wood. I think we have to realize what a joke this is, because today the amount of timber we use is about 5% of the amount of cement. And in fact, we're already cutting down more forests than we're planting. So we need to plant more forests. I've just heard here how Cementos Progresso is planting more forests. But if we wanted to replace just 1/4 of cementitious materials with timber, we would have to plant new forests 1.5 times the size of India. Now that's clearly going to be a good thing to do, but even if we did it tomorrow, we'd have to wait more than 30 years for this to produce timber. So on the horizon of 2050, which is what we're looking at, timber cannot do anything more than it's doing already. And most people have this very negative image of concrete, thinking this is a high energy material, but this is also completely wrong. It does account for this 8% of CO2 annually, but this is only because we use such enormous quantities of it. As you can see in the graph in the top right, it has lower emissions than almost any other material. And we're not going to help anything by turning to things like clay bricks or things like this, because these have much higher emissions. So we can get a lot more by making concrete better than we can by switching. The second message is to see how the pattern of cement use is totally changing. So in the last 30 years, we've seen development in China, which has really driven the demand for cement, such that China today is now consuming more than half the cement produced in the world. And in the next 30 years, the demand in China is going to go down because they've built all their rail networks, and they don't need to have so much cement per head. But this demand is going to be taken over by the developing regions of the world, like Latin America and Africa, etc. So we need solutions for people in developing countries. Now, I haven't got time to go into all the arguments on it, but if you're interested in this, there are some videos online where I present all this in detail. But if we analyze the composition of the Earth, we can really see that this composition we call Portland cement is an inevitable consequence of the chemistry and geology of the Earth. So there's no alternative that can be produced in the quantities needed. That doesn't mean we can't do anything, because what we can do, and what we're talking about in this LC3 technology, is replace a large fraction of this with other materials which are called supplementary cementitious materials. The problem is that the supplementary cementitious materials we've been using mostly to date are things like fly ash and slag. And there's two problems there. First of all, even today, the amounts of these materials is really limited. Together, they probably only make up about 15% of current cement demand. But the second thing is they both come from very carbon-intensive processes. Fly ash, for example, comes from burning coal, and that's the very first thing we have to do to confront climate change, is stop burning coal. So fly ash will disappear. It's already not available in many countries. And slag, similarly, this is coming from reduction of iron in blast furnaces. This is a more CO2 intensive process than making cement. And again, people are looking at alternative ways to produce iron, looking at more recycling. So the amount of slag will go down. So slag in particular, is a very effective SEM. You can replace 70% or more of cement by slag, but worldwide we only have 8% of slag compared to cement. So now, if you want to use more slag in one place, you're just taking it away from another place, because 95% of that slag is already used. So where else can we go? Well, we've got a lot of limestone, but the problem with limestone is really very, very slightly reactive. And therefore, if we go above substitution levels of about 10–15%, we'll simply have a dilution and we have to end up using more cement. What we have got is clays, and clays we can calcine, that's to say heat to around 800 degrees, and then they become very reactive materials. And because they're very reactive, you can go to high substitution levels. So you can go to much higher substitution levels than you can do with, say, fly ash or natural pozzolans. So there's no magic solution. Blended cements with supplementary cementitious materials will be the best solution for sustainable cements for the foreseeable future. And the only material available in viable quantities is clay, which can be activated by calcination, that's to say heat to about 800 degrees. And what we discovered, which is the essence of this LC3 technology, is there is a synergetic reaction between the calcined clay and limestone, which allows you to go to very high levels of substitution. And this led to what we call the LC3 project, which was supported by the SDC, the Swiss Agency for Development and Cooperation, since 2013. And this QR code will lead you to a nice brochure, which I'm sure Fernando has copies with him there today, but you can look up more details on that. So essentially what we're doing with LC3, we're replacing a large part of this clinker, which is what produces the CO2 emissions, by a combination of calcined clay, which has some emissions from the calcination, but these are much, much lower than clinker, up to 10 times lower, and limestone, which essentially has no CO2 emissions. So this is the mix we call LC350. This means it has 50% clinker contents, but in some applications you can even go to lower clinker contents of at least 40, down to 40% or maybe even lower. But what's really interesting is even though you've got these very high levels of substitution, and this is unlike most other pozzolanic materials, you get the same or better strength. So we have slightly lower strength maybe at 1 day, but we have higher strength already at 7 days. And in fact, even in this example here, the strength was slightly lower at 1 day. If you have good grinding technologies, you can even meet the same strength at 1 day. And this cannot be done with other substitute materials. And, 7 and 28 days, this is higher. So you've got 50% or even more fewer clinker. This amounts to about 40% of CO2 reductions, and you have similar strength and some properties like resistance to chloride penetration, which is obviously very important when you have structures in seawater, and resistance to alkali silica reaction are incredibly improved. So of course the main question is what kinds of clay are suitable, and I know Fernando will talk a lot more about this in the day today, so I'm not going to go into a lot of detail. But in essence you need about 40% kaolin, and these materials are very widespread. So you're not competing with other applications like metakaolin, which is used to coat paper, used for ceramics. We're not talking about this, we're talking about materials with just with a relatively small amount of kaolin. And the reason kaolin is so interesting is because it has this so-called one-to-one structure where we have a layer of silicates and a layer of alumina, and during the calcination process this crystal structure becomes disrupted and both the silica and alumina are available to react. And the alumina is the alumina content that reacts with the limestone in this synergetic reaction. And these kind of clays are really very widely available. So these maps show the main clay type in different areas. What we're looking for is the areas that have this kind of yellowy orange color, which is related to kaolinite as the main clay type. And you can see it's really abundant, and particularly in those parts of the world where development is occurring most strongly, like in Africa, like in South America, Southeast Asia, India, etc. But we also have quite large deposits in the USA and even in Europe. And if we zoom in a little bit on the region where you are now, you can see all around here very nice clay deposits. So this is really a technology which is mature. I mean, we've built houses. This is the first house we built about 9 years ago now. I think we opened this house in 2014. And we could show that this house saved around 14 tons of CO2 compared to even existing solutions with fly ash, for example. And we can look at these different kaolinite types by looking at the weight loss. I won't talk much about this because I'm sure Fernando will talk in detail, and we can see the compressive strength correlates with the strength development. So when we look at calcination of the clay, the important thing, this can be achieved with existing technology. We can use rotary kilns, we can even use adaptive clinker kilns, and flash calcination, and the emissions can be as low as 900 kg. 900 kg, but in the range from 1 to 200 kilograms per ton. And I think in the medium term, we can even see that these kind of calciners can be possible to electrify. So this is an example of one of the first plants which was built in the Ivory Coast. I'm sure you'll hear a lot more about this from the manufacturers today. But what was really nice in this plant is that they could really demonstrate that it's possible to control the color. Because when we first started talking about calcined clays, many people were saying, well, we don't want this red color. People don't like red cements. Well, in some applications, red cements could be quite good, but never mind. If you want gray cement, you can have gray cement quite easily. And the key advantages, as I said, are chloride resistance, suppression of alkali-silica reaction. I'm not going to show you any results about alkali-silica reaction because there are no results. There are no expansion in any of the specimens we've tested, even out to 9 years of testing now. But on chloride resistance, we can compare. Here we've compared many different mixtures. We have the reference ordinary Portland cement here in black, and you see after only 6 months, the penetration is almost right through the sample of 40 millimeters. Then we have two mixtures with slag and limestone. These are somewhat better. We have two mixtures with fly ash and limestone. These are better still, but the best mixtures are with the calcined clay, and the best of all is with the calcined clay and limestone. And with the calcined clay and limestone, we have an apparent diffusion coefficient, which is about 10 times less than the reference. So this will mean a very, very substantially increased service life in chloride environments. Now, the reasons for this, we start to know in a lot of detail, is partly due to the refinement of the pore structure. It's partly due to the lowered amounts of alkalis in solution, but it's also to do with how the calcium silicate hydrate changes in blended cements. Again, I think this is a topic where Laurent is going to talk more about the financial advantages, so I'll not go into this in detail, but to cut a long story short, in many, many scenarios, you can make these materials more cheaply than you can the reference Portland cement. So the potential for this technology is really enormous. This graph here shows the average level of cement substitutions around the world, and this has really stagnated for the last 10, 15 years. And the reason it's stagnated is because of this shortage in the availability of slag and fly ash. So if we remove this shortage coming from just using slag and fly ash, and we bring calcined clay into the equation, I think we could quite easily increase the substitution level to about 40%, and this would represent saving about 400 million tons of CO2 per year. But on a horizon of 2050, I think we could even do much, much better than this. We could go to a substitution level of something like 55%, which would represent a saving of 800 million tons of CO2 per year. And to put that in perspective, this is like 20 times the emission of Switzerland. I know Switzerland's a small country, but it is a country where every person has an extremely high carbon footprint. So this is a very, very considerable amount of CO2. And I'm very pleased to say that we're working with all these different countries around the world, and this really means that, we can have a big influence. And just going back to something that was discussed in the last presentation, I would emphasize that LC3 is not a startup. We're not a company, because we realize that to get CO2 reductions on a large scale, you need to have technologies that can be adopted in the over 3,000 cement plants around the world. And for that reason, all our research is in open source, it's freely available, and there are no patents blocking applications in nearly every country. So this really is how we want to continue to develop in an open source way, and we hope you'll join us here. This is a nice new building that they're planning to build in India, which shows that really we can use this on full-scale structural applications. And a short summary here of the advantages of LC3. You're saving CO2, you're saving scarce resources. So often, limestone is coming in short supply in many areas. You can get twice as much cement from the same amount of limestone. You have similar or better performance than OPC, and you can scale this really to the global demand. You can save costs in production, and it can be used in all the range of applications with no special training or equipment needed. So thank you for listening to this presentation, and if you have more questions, I'd be happy to answer these.
Thank you very much, Karen. As you know, we're using this Slido online system platform for questions, and I have 5 questions, and we have time. We have time to do them all. The first one is how do calcined clays compare with fly ash and slag?
Well, basically they compare extremely well. Calcined clay is much more reactive than either of these. So, I should have included this slide, but, we have a comparison with different mixtures, and in long terms, they all have about the same strength, but the strength of the LC3 systems is developed much more quickly. So you can, as I showed, you could even have the same strength of 1 day as a Portland cement reference, which you certainly can't do with either of these other materials. In terms of the absolute level of replacement, LC3 is comparable to slag, that you can go to a level of replacement of 60% or even higher. You certainly can't do that with fly ash or natural pozzolans. The limit, you can only go to about 20 or 30% replacement with these materials.
Thank you, Karen. The second question is, calcined clay will create calcium aluminate hydrates with calcium hydroxide from the clinker. How does limestone create synergy with that reaction?
Yes, so what you have the formation of calcium aluminate, of carboaluminates. So you have monocarboaluminates and hemicarboaluminates. These phases already form in Portland cement because most Portland cements today contain small amounts of limestone, 4 or 5%. And so these phases are already present in those systems, but with the LC3 system, you get higher amounts of these phases. And these have all been well characterized in our work. We have many publications in scientific journals which explain these phases and what they do and everything like that.
Thank you. Next question is, what is the quality control to the calcined clay?
Well, I think you'll hear more from that in the other presentations today. There's 2 things you need to look at. You have quite a broad temperature range from the calcination, between about 700 and 850 degrees. It's really all pretty much the same. And the 2 things you need to control, one is under calcination, and this you can do by looking at the weight loss to check you have no kaolin present. And the second is over calcination, and this you can check by various techniques. This is also an ongoing subject of research. So we have a lot of techniques which can detect these, but what we really need is very fast methods. And this is being studied in the Innovandi project with Global Cement and Concrete Association. And there will be better and simpler methods very soon. And I think probably Fernando can talk a bit about it. We'll talk a little bit about this later.
Thank you, Karen. Next question is, in your opinion, what or which are the incentives for companies to opt for calcined clays?
Well, I think there's 2 big incentives. The first big one is, CO2. So all companies which are members of the GCCA have committed to reaching net zero by 2050. Basically calcined clay is the cheapest way to get there, because otherwise you've got to go to things like carbon capture and storage, which are going to be incredibly expensive. The second one is that you can actually save money. So as I showed briefly, but as I know Laurel will talk a lot more about later today, you can produce this material more cheaply, so you can save money, but you can also extend your resources. So if you have an existing limestone quarry, you can make the lifetime of that quarry twice as long. So there's really lots of incentives for companies to do this, and I think these incentives are only going to increase as we see things like carbon taxes coming and other incentives to push people to reduce CO2.
Thanks, Karen. Well, we have a lot of questions. We still have 3 more
Yeah.
questions, and we have time to.
You have the whole day there, so I'm sure
Yeah.
you're going to come back to many of these questions
Okay.
later on in the day.
Next question is, did you test the long-term durability of the concrete produced with LC3 cement, and how?
Well, we've only been producing this 10 years, but we have samples now 10 years old, which are all performing very well. I think more importantly, we now have a huge range of methods for looking at durability, such as the chloride ingress I showed you earlier. And we see that this, compared to existing materials, the performance is really excellent. I think the third thing, which is very important, is we understand all the mineralogy and microstructure. So we have the same phases present in LC3 systems as we do in other blended cements. We've been using blended cements with slag and fly ash for many decades now. And basically in the LC3 system, we have the same hydrates there. So we can be really confident that these behave very well in the long term.
Thank you. The next question is, how many LC3 projects are currently going into application, into a real world?
I think today we have about 6 plants around the world producing LC3. One of the biggest now is the new plant that just opened in France, just outside Paris, which was announced by Holcim only a few weeks ago. But we know there's many, many others in the pipeline. I think we have pretty firm figures for what's already under construction, that there would be at least 20 plants operating by 2005. But I think the uptake is going to be very fast after that. My target is to have at least a few hundred operating by 2030, and I think that's realistic.
Well, that's really challenging. And the last question is, how is the carbon market reacting to LC3?
Well, I don't think you can say the carbon market has a specific reaction. The carbon market is like, you're going to get taxed on the CO2 you produce. And if you produce less CO2, you pay less tax. In Europe, we've had these carbon taxes for quite a long time now. But now the price per ton of CO2 is really taking off. And this is going to be a trend that's only going to continue. So I don't think you can say the carbon markets have a specific reaction, because they're concerned by all sectors of the industry, etc.
Well, I think this is all. I thank you for your time, for your participation, and again, despite the distance, we were able to connect with you, and really appreciate that you make this presentation, respond to the questions. Please. You can stay online if you want. Sorry. Go on.
I was going to say thank you for letting me join, and all my best wishes for the rest of the day.
Thank you.